Welcome back to the lecture. In the last lecture, we have seen the passband transmission model, where I have a message recap. Passband transmission model. I have a message MI to transmit. So it can be M1, M2, M3, etc. I have M message symbols to transmit. So that is converted to a signal SI of t and then transmitted to the channel and received as X of t in the receiver, and from this I will be estimating my signal, a symbol M cap of t. Okay, so I send some symbol as a signal through the channel where a noise is getting added, and I receive X of t. From that I estimate the symbol t, estimate the symbol that I have transmitted. This is the basic passband transmission model. Why it is called passband? Because we are not transmitting the signal that is representing the symbol MI directly to the channel, but we modulate that to a carrier. So MI first, in baseband transmission, MI is converted to some AK, okay, AI of t, okay, a low pass signal, and then directly transmitted to the channel and received. But here this MI is converted to this, and then you modulate that to a carrier and then transmit. That's why it's called passband transmission. Okay, and we have seen in the last class that we have two different schemes: coherent modulation and non-coherent modulation in passband transmission model, where coherent needs the phase information for the demodulation, and in non-coherent we don't need the phase information for the demodulation. So we discuss binary phase shift keying method of modulation. Okay, first, this is a coherent modulation scheme. That means to detect the signal back, I need the phase information in the receiver. Okay, so what is a BPSK signal or BPSK modulation scheme? I have a symbol MI to transmit. Okay, here what are the symbols that I have? I have only two symbols. That's why it's called binary phase shift keying. Okay, I have only two symbols to transmit, M1 and M0. Okay, this is my symbol M1, this is my symbol M0. Now how I am going to transmit these symbols? To transmit M1, I'll be sending a signal, a high frequency signal, S1 of t. Okay, to transmit M0, I'll be sending a high frequency signal, S0 of t. Both are shifted in phase by pi. Okay, this is root 2 EB/TB divided by TB cos 2 pi FCT. Here same, but cos 2 pi FCT plus pi. So the information is contained in the phase of the carrier signal. How we detect the information? So simply by looking into the phase of the carrier. So if this is the carrier, then it is 1. If this is the carrier, then it is 0. So you can simply use the identity cos theta plus pi is equal to minus cos theta and get this equation, minus root 2 EB/TB cos 2 pi FCT. Now the next information is this, that is to ensure that each transmitted bit contains an integral number of cycles of the carrier wave. The carrier frequency Fc is chosen equal to Nc by Tb for some fixed integer Nc. So what does that mean? It means that you are sending either 1 or 0. For example, you are sending 1. Okay, this is your 1. So this is 0. So this is your simple. So here you are transmitting 1, here you are transmitting 0. Now for 1 you will be transmitting a high frequency cosine signal, right? For 0 you will be transmitting a high frequency cosine signal shifted by pi, right? Now the point is that when you transmit a cosine signal corresponding to this 1, you should have an integer number of cycles of that signal in this interval. That is, for example, I have said this is a cosine signal. Okay, this is a cosine signal, and this is another cosine signal. That means I have 2 cycles of the cosine signal in this bit duration, you can say. So in this bit duration I have 2 cycles. Or if I increase the frequency, I may have 3 cycles or 10 cycles or 100 cycles, 1000 or 10,000 or 10 to the power 6 cycles. Okay, but it should be an integer number of cycles or integral number of cycles. It should not be like 1.5 cycles or 2.3 cycles like that. So to ensure this, that is, each bit duration contains an integral number of carrier wave cycles, I'll be choosing the carrier frequency like this. Okay, Fc is chosen as 1 by Tb. 1 by Tb is simply the inverse of this interval. Okay, something like a frequency of this bit duration. So that is my carrier frequency is an integral multiple of that frequency, so that I will have an integral number of carrier cycles in a bit duration. Okay, now you consider this equation number 1. So I am writing it once again here. S1 of t is root 2 EB by TB cos 2 pi FCT. Okay, now simply take this root EB outside. That is root EB root 2 by TB cos 2 pi FCT. Now if you say, and I am naming this as phi 1 of t. Now if you find the energy of this phi 1, that is E phi 1 is integral 0 to TB phi 1 of t square, okay, dt. This is 2 by TB integral 0 to TB. This is cos square 2 pi FCT. Say let me call this as cos theta. Okay, so this is cos theta. 2 pi FCT is theta, cos theta. For simplicity I am considering this as theta. So I have this square, so 2 by TB cos square theta. Cos square theta is nothing but 1 plus cos 2 theta by 2 dt or d theta. Since I have substituted t theta here, I have d theta here. Now you have 2 by TB into, so 1 by 2 d theta, that is nothing but 1 by 2 TB when you evaluate that integral, plus integral cos 2 theta by 2 dt d theta, that is equal to 0 because cos function has equal positive and negative part. So if you integrate that, you will get 0. So this is equal to 1. That is, energy of the signal phi1 is 1. Means to represent these two signals, okay, S1 and S0 in signal space, I need only one basis function, which is phi1 equal to this root 2 by TB cos 2 by FCT. Okay, I need only one basis function to represent these signals in signal space, where the coefficient S11 is root TB and S01 is minus root TB. So what is the coefficient? Okay, what is coefficient? S11 is nothing but inner product between the first signal S1 and the basis. Okay, so you can do that way also. Okay, you can find this inner product, but simply by looking into this equation, you can find that S11 is root EB, because so except this root EB, the other part of this equation is phi1. So this is equal to root EB in phi1. So what comes with phi1 is actually S11. And similarly, you can find S01, which is minus root EB. Now this is the graphical representation of BPSK signal space. Okay, so signal space diagram or constellation diagram simply. So this is my basis, so I have only one basis. Okay, so it is a 1D signal space. Okay, one dimensional signal space, because I have only one basis. I need only one basis to represent the signals that I transmit. So this is a one dimensional signal space. So n is equal to 1, and you have two message points. So two message points corresponding to S0 and S1. So this is my message point 1. This corresponds to my message symbol M1 or signal S1, and this is my message point 0. This corresponds to my message point M0, and this is my constellation diagram. Now the signal vector S1, okay, S1 have only one element in it or one point in it, because I have only one basis. So the signal vector has only one element in it. So S0 is root EB and S1 is root EB and S0 is minus root EB. Okay, so this is just an introduction to the binary phase shift keying. In the next classes, we will see the probability of error in the scheme, as well as how to generate a BPSK signal and detect that. Thank you.